This lecture is about permutation feature importance. Here we want to understand how permutation feature importance, or PFI, is computed, understand its strengths and weaknesses, and also talk about statistical testing of importance values. So what is permutation feature importance? The idea is to destroy a feature of interest xj by perturbing it in such a way that it becomes uninformative. So for example, we randomly permute all observations in feature xj, but then the marginal distribution stays the same. So in more detail, the PFI for features xs, now S is a set of features, but for now assume that this is just a single feature, and we use test data D. So now we once measure the error without permuting the features and with permuting the features. We call the permuted version xs tilde. And we repeat that m times by calculating the empirical risk, so the loss of our model, using ds tilde k. So that's the k is permutation of our feature S, of our feature set S, and that gives us the data d tilde sk. And we also calculate the loss of our model using the original data d. And we just average this m times. And that gives us the permutation feature importance estimate of our feature set S. And for the empirical risk, here on the right, we can just use the loss function and average over all observations in the dataset. So for example, we have the data D and have our original feature XS, replace it with a permuted version XS tilde, and call the dataset DS tilde. And if we have S equals a set of 1, so only feature 1 is in our set of features of interest, and M6, so we have 6 permutations we want to do. Then we start with the original data set and we permute the feature X1. And if we only have 3 observations, we have 6 possible permutations. So the first one would be to actually not permute, and then we also have 5 other options. And we so in this simple case of only 3 observations, we can just look at all possible combinations. But usually this is not possible because we have larger numbers of observations, and that is why we just sample m random permutations and not take all possible ones. And note that S here is a subset of features, and we just only calculate it for a set size of 1. But we can quite easily not only permute 1 feature, but also permute 2 features at a time. So then we would permute this feature and this feature. But in most of the cases, you just use it for 1 feature. So let's do this calculation by example. So we start with our original data set, and now we permute XS, so here this is X1, and by that create our data set TS tilde K. So that's the perturbation. Then in the second step, we calculate the loss on our permuted data. So that gives us for each of our 3 observations a loss, and we do the same for our original data. And now we look at all the differences. So first we do the prediction. Sorry, this was not the loss, but the prediction. And now we do the loss calculation. And that gives us a loss for the permuted data and a loss for the non-permuted data. And now we look at the differences. And now all the differences give us, for each observation, 1 value of the loss difference. And if we average that, this is the permutation feature importance. And note that we could also first do the averaging. So we could average those and those, take the difference, and that would lead to the same value of our PFI estimate. And now we do that several times. So not only once. The first is the permutation we just used. The second case, we use here another permutation. Everything else is unchanged, but that gives us other loss differences and also another PFI estimate. But in the end, we just average all the PFI estimates of the different repetitions. So to give you an example, let's look at the bike sharing data. And here we have, for all the features, we have one value for the feature importance and some quantiles over the repetitions. So it seems like the two most important features are year and temperature. And the interpretation is that this value here is 816. So that means that permuting year would decrease the mean absolute error, would increase the mean absolute error of the model by 816. So if we permute it, the model gets worse. And that's why year is important for the model, for the prediction. And we use the 5 and 95% quantiles of the repetitions to show the error bars to get a sense of the variability of the PFI estimate. So some comments on PFI. So the interpretation is the PFI is the increase of model error when features information is destroyed. But results can be unreliable due to random permutations. And the solution here is to average over multiple repetitions, which also gives us the advantage that we can, for example, plot those error bars and see the variation. But the problem is that permuting features, despite correlation with other features, can lead to unrealistic combinations of feature values. And that's because if two features are dependent, then the joint distribution is not the product of the marginal distributions, and that leads to the extrapolation issue. So we'll revisit that several times, but I will also explain it in more detail later. So PFI automatically includes importance of interaction effects with other features. So if we permute one feature that destroys the information of that feature, but also destroys all interaction effects with other features. And that because of that, the importance of all interaction with the permitted feature is contained in the PFI scores. And that also means that we see all interactions twice, but we'll also see that in a minute in an example. And the interpretation of PFI depends on whether training or test data is used. So also more on that soon. So let's start with the extrapolation issue. So let's take a very simple example where our target Y only depends on the feature X3 and some random error. And now X1 is just noise and X2 is X1 plus noise. So those two are very highly correlated. And then we have X3, which is noise, and X4, which is noise. And all noise terms are independent. If we now fit a linear model on that, it will give us a small effect of X1, a small negative effect of X2, and a larger effect of X3. So those two here cancel each other out. And the reason is that these two are highly correlated, and the linear model has problems with that multicollinearity issue, and it can assign any arbitrary value to X1, and it can just cancel it out with the same negative value for X2. And if we now calculate PFI on that, or first, if we look at X1 and X2, we see here that they are quite highly correlated. So it will not happen that you observe a value of X1 of 2 and a value for X2 of -2. So there's no data here. But now, if you permute X1, you will get all values in the of the marginal distribution of x1. And this is between -3 and 3. So what happens is that this correlation is destroyed and you get data like this. What happens is that you also get here those very unrealistic data points. Actually, all data points not on this diagonal are quite unrealistic. And that means that also x1 and x2 get a high permutation feature importance. So x3 correctly gets a high value, but x1 and x2 actually have no effect on. So if you look here at the data generating process, it's only x3, but x1 and x2 also get quite a high PFI value and are considered relevant. And the reason is that the PFI, that's this here, evaluates model on the unrealistic observations outside of the joint distribution of x1 and x2. So a very easy example here would be if, let's say, x1 would be age of people and x2 would be weight of people. And now you will have, if you permute one of the features from the marginal distribution, then you might end up with babies weighing 80 kilograms, for example, because you might permute the weight feature, but not the age feature. And this gives you then this very unrealistic observations. So the next issue is interactions. So let's again look at an example. So let x1 to x4 be independently and uniformly sampled from -1 and 1. And our target is now an interaction of x1 and x2 and a feature x3 with an effect of 1. And if we correctly specify a linear model, it will give us the true data generating process. But if we now use permutation feature importance on that linear model, we will see that x3 gets a high PFI, but also x1 and x2. And the reason for that is that if you look at this interaction effect and you permute just one of it, then the whole interaction is gone. But if you instead permute x2, also the whole interaction is gone. So you see the interaction twice, once in the effect of x1 and once in the PFI of x2. So PFI does not fairly attribute the performance to the individual features, which is different, for example, in Shapley values, as we'll see in another lecture. So then we also had the issue of test and training data. So we again do an example and we have 20 features and we also have our target Y and it's all independently sampled. So there's no effect of the features on the target. And we fit an XGBoost model on this data with just 50 observations. So the model heavily overfits. And what we see is that on the training data, we see strong effects of the features. So just of random features, because it's overfitting. The model selects any features, overfits on it, and if we look at the training loss, then destroying these features will increase the error, the training error. And that's why we get high PFI values. But permuting those features won't change the testing error. And that's why the PFI on test data is always 0. And now it depends on the interpretation you want to have. So if you really want to do, really want to know what the model is doing, then you might want to look at PFI on training data, because actually for the model, those features are important. But if you want to see how well does those features help the model to generalize, you should use the PFI on test data. So let's relate the PFI to the 3 different interpretation goals we discussed earlier. So the first was feature xj is causal for the prediction. So here a PFI value for feature j, which is not 0, means that the model relies on xj. So that means, yes, the feature is causal for the prediction. But in the other direction, it does not hold. So if the model relies on xj, it doesn't have to mean that the PFI is different from 0. So for example, in the training and test data example, we have seen that on the test data, PFI is 0, even if the model relies on xj. The second interpretation was feature xj contains prediction relevant information. So here, if the PFI is different from 0, then that means xj is dependent of y or of its covariate x minus j, where x minus j are all other features than the feature of interest j. And because of the extrapolation, it doesn't have to be that xj is dependent of y, but it can also be just to the covariates. And if xj is not exploited by the model, so for example, it's never splitted on in a tree-based model, then this means PFI is 0. So it could be that the feature is actually useful for the true target, but the model never used it. So if the model cannot detect the effect, PFI can also not detect the effect. And the third interpretation was, does the model require access to xj to achieve its prediction performance? And here we have seen in the extrapolation example that such insight is not possible. So it might be that you have two features and one feature could just replace the other one. So they could basically have the same information. So a feature might be important for the model, but that doesn't mean that the model needs exactly that feature. So finally, about statistical testing of feature importance. And we'll use the PIMP. So it's also an abbreviation for permutation importance algorithm. And this was originally introduced just for a random forest built-in permutation feature importance, but you can also apply it to the model agnostic permutation feature importance. And the question here is the PFI score significantly different from 0? So the problem is you might have a PFI value which is larger than 0, but you don't know, is this just because of the randomness of the whole process, or is it a true effect? And the statistical test, you want to see whether this is significantly different. And for that, you test against the null hypothesis that the feature is independent of the target y. So your null hypothesis is feature xj is independent of y. And your alternative is feature xj is not independent of y, so it is dependent of y. So what you do is you want to do sampling under the null, and for that you permute your target y, retrain your model, compute PFI scores, do that repeatedly, and because the permutation of y is breaking the relationship to all features, you are actually under the null. And by now computing the PFI scores again several times, you can get the distribution of the PFI scores under the null. And now you compare your observed PFI value with the distribution. So you look at the tail probability under the null and use this as a new importance measure. So in detail, the algorithm is for n repetitions. In each step, you permute the response vector, you retrain the model with the original feature data X and you permuted Y, and now you compute the feature importance PFI JM, so a feature J of the M repetition for each feature J under the null. And in the second step, you train your model with X and an unpermuted Y. And for each feature, you fit a probability distribution of the feature importance values, so of the one under the null. And you can do that in parametrically using, for example, Gaussian or log normal or gamma distributions, or in a non-parametric way. So by using quantiles, for example. And now you compute the feature importance for each of the features without permutation of Y. So that's under the alternative if actually the performance is larger than 0. And you retrieve the p-value of the PFI based on the fitted distribution. So let's look at that in an example. So remember our example from before where we had the target Y, which is just an effect of X3, and we had X1, X2, which are highly correlated, but independent of Y. And X4 is independent of all others. And we had that linear model where the two effects cancel each other out. And if we now replace histograms of the importance under the null in gray for X1, X2, X3, and X4, and plot in red the actual observed PFI score. And we see that for X3, it's quite clear. So the actual value is here. The null distribution is somewhere here. So it's quite clear that this is far apart. So it's even more than in the tails. So this is clearly significant. That's also why the p-value is 0. For X4, it's also quite clear. So we have a distribution which looks kind of normal. And we have the observed value right at 0. So that means it's also far from the tails and gives us a p-value of about 0.5. For X1 and X2, it's a little bit strange because we don't observe negative values. That's because of the correlation between the two. But we also see that in the tails, the permutation feature importance would have to be here somewhere at 10, but it is actually quite a small value. And we observe about the same for X2. And that's why both p-values are quite large, because we're not in the tails. And the X1 and X2 are not considered significant. But the problem is, if you have a high dimensional problem and you have many features, then when should we reject the null? If you just would do that often enough, so look at many, many features, then you just by chance, because of the type 1 error, would find some false positives. So this is called a multiple testing problem. And you want to be careful to not get too many false positives. So to not have a too high type 1 error by rejecting too many null hypotheses. And there are several options to deal with the multiple testing problem. And then one of the approaches is to control the family-wise error rate. So that is the probability of at least one type 1 error. And the simplest solution to that is called the Bonferroni correction, where you just take your significance level from the beginning, so it might be 0.05, and you just divide it by the number of performed tests. So if, for example, you have 0.05 and you have 100 features, then you would say your unadjusted alpha is 0.05 and your alpha adjusted now might be 0.0005. So now the p-value would have to be smaller than 0.0005 to be considered significant. Or you could, that's actually exactly the same, also just multiply the p-value by n. But there are also many more options. Some of them are not as conservative as the Bonferroni correction. So this is quite a quite a stringent restriction to only consider those p-values that small as significant, and it's often too strict. And that's why we also have other methods which are a little bit more liberal, but we won't cover them in this lecture.